All right, so our next talk will be by Nairen Cao, talking about breaking three-factor approximation for correlation clustering and polylog rounds.
Okay, hello everyone. So I'm Nairen, so from NYU Tandon. So here I'm going to share my work about the correlation clustering in the parallel model. Thanks for having me in this workshop. It's a pretty wonderful workshop. And this work is a joint work with my collaborator. They are very brilliant, Shang and Xin Hao. So first, what is the correlation clustering problem? So in this problem, we are giving a complete graph. So the graph is complete, okay? So each edge is either positive or negative. You can think positive edge as two nodes, they are similar. Negative means they are dissimilar here. So usually we only show the positive edge, show the similar item here. So I ignore this negative edge here. So, but if I use a red edge, it means a negative edge. Then once we have this input graph, what's the target for this problem? We want to partition this node into a lot of groups, which minimize the total disagreements. What is the disagreement here? So it will be the positive edge in different cluster. Positive edge means they are similar, but we separate them. So it's a disagreement. Or it's a negative edge. They are dissimilar, but we put them together. This is one disagreement. So we want to minimize the total number of this disagreement. This is the target. So in this problem, the number of the partition is not given. So we can use this to do some unsupervised learning. This is one advantage. So it's different from k-means, where k is fixed here. So in this example graph, what happened? So here is the optimal solution. We will have four partitions. So in most of this partition, we will put similar nodes together. And the disagreement for this graph, there are three positive disagreements between this AD, CO, and CF, three positive. We also have another negative disagreement, which is between AR. So I draw it explicitly here. So the optimal value for this instance is 4. We want to figure out what is the minimized value for the disagreement. Okay, this is a problem. So I'm going to give a little bit motivation here, how we can use this correlation clustering problem. So this is also given by my collaborator here. So one application, there are a lot of page has maybe the same name, but they are different person, Michael Jordan. So we want to figure out which page refers to the same person. So we might extract some page from IMDb. We will have a basketball Michael Jordan and then actor Michael Jordan. Maybe actor is not that famous, you don't know, but we have this actor. And then we might get some wiki. So we also have the Michael Jordan from Berkeley. I think he just moved, right? So he's famous in academia. And then we also can get some Google Scholar. We want to figure out which page refers to the Google Scholar page. So Google Scholar person here. So what we do, we first run some algorithm trying to figure out which page are related or not. So for example, we figure out that, okay, in the IMDb, there is this actor page related to this wiki page. In this process, we may make some mistake. For example, this actor, Michael Jordan, we related to the basketball. It's wrong. So we need to do something extra. So we can run our correlation clustering problem. Intuitively, this correlation clustering algorithm will group the same person, the page under the same person into one partition. So although there might be some errors, but it will ignore this error in the algorithm. So at the end, we can do this clustering and figure out which page refers to the same person. That's the motivation why we care about this problem. Okay. And before going to the related work for this problem, so you may wonder, what's the result for different versions? What if we have general weight? Okay, here the weight is positive or negative is unweighted. What if we have a weight for each edge? Or instead of considering the minimized problem, we consider the maximized problem. We maximize the agreement. So unfortunately, for all other 3 problems, it's either solved or it's super hard. For example, if you care about the general weight graph, so if the graph has weight, and we consider trying to maximize the agreement. So in this problem, it has been shown that we can use some SDP method, semi-definite programming method. It's quite similar to the max-cut algorithm. And we can use the SDP, get an optimal solution. So it's already solved. For the mean version of the general case, so it has been shown that this algorithm actually is equals to multi-cut problem. So for multi-cut problem, the best possible is order log n approximation ratio, and it's believed this is the lower bound. And also for the complete case, if you consider the maximum version here, so it's already shown there is a p-task. So this is the best we can hope. So there is nothing we can do for these other 3 cases. We can only try to do something for the mean complete case. So one thing for this is that in the parallel model here, although in the sequential setting, those results are well studied, but there are very few results for the other 3 cases. So maybe it's an interesting direction. But this talk, let's focus on the mean complete graph. So the graph is complete. Okay, this problem is formulated, I think, 20 years ago. So once it's formulated, it gets a lot of citation. So if it's just TCS people solve this problem, it won't be so many citations. So I believe some machine learning people really use this algorithm. And this problem is shown by Charika, Guruswamy, and Ross. So they show it's NP hard. So it's impossible to get the exact solution, okay? So we can only hope for some approximate solution here. And they even show it's APX hard. So what is APX hard here? It means no algorithm can achieve 1.01 approximate ratio in polynomial time, okay, under some assumption. So we can only hope we can get some approximate ratio, and not that there is no p-task for this algorithm here. So, and in the sequential setting, okay, this is the sequential setting. And it has been shown that the best approximate ratio currently is 1.437 here, okay? And there is a gap between these 2 things here, but it's not that much, this gap. So in the sequential setting, it really has been well studied. So, and actually, if we consider the parallel algorithm, or finally we have the parallel algorithm here. So you are not going to run this algorithm, run the sequential algorithm in single CPU here. So we have to take advantage of the GPU or CPU. Here, when we consider the model of the MPC, so actually the parallel model does not matter so much here. So for MPC or for PRAM model, so you can easily transform one algorithm in MPC to PRAM, or even to the streaming or to the local model. So the parallel model really doesn't matter so much here. Here we consider the sublinear MPC model. So, and there are a lot of work trying to get better approximate ratio and also runs. You can think the runs as the depths. Get a better approximate ratio and the runs. So you can see all of this approximate ratio gets stuck at 3. They can even achieve 1 round algorithm. So you just need 1 round MPC. So in the MapReduce model, you can get a very good approximate ratio here. But for the approximate ratio, for the solution quality, all of this solution can only get 3 approximate ratio. So this is a bottleneck in the parallel algorithms. Can we achieve better than 3 approximate ratio with reasonable runs? Okay, this is our question and the bottleneck. So it's natural to ask whether we can achieve a small round parallel algorithm that has a good approximate ratio. I will explain why this algorithm gets stuck at 3 very quickly. But here, let me explain our result a little bit. So we answer this question, yes. So we can get a poly 1 over epsilon and the log runs. And this algorithm achieves 2.4 plus epsilon. This epsilon you can think of some constant. 0.01, so 1 over 100. This is a p-rank algorithm using tilde order m to 3½ work. So m is the number of the positive edge in the graph. Okay. You can easily transform this algorithm to MPC model. So it has to take order m to 3½ memory. This is one drawback of our algorithm. So usually the MPC algorithm will only use order linear memory, order m memory. But our algorithm has to take slightly more than linear. So this is bad. But the advantage is our algorithm is depth is very slow. Maybe some people won't agree. So more precisely, this poly 1 over epsilon log is log n to 6 over epsilon 7. I don't do coding, so maybe I'm not sure whether we can run this algorithm with some code. So maybe it's not runnable. Okay, but we claim this is very cheap in theory. Okay, just in theory. You will see why I say this. There is a much constant algorithm very soon. Okay. So this is our main result. Low depth algorithm with better than 3, 2.4 plus epsilon. And actually, after our work, there is a new work achieves 1.847 approximation in this MPC model, and their runs is constant, is 2 to the poly 1 over epsilon. You can think 1 over epsilon is 1/10. Okay, so and we count this poly 1 over epsilon in their paper is at least 1 over epsilon to 162. So if you plug even half, this is 2 to the 162. So, but it's still constant in theory. So it's a better algorithm, better than our algorithm. So you see that we cannot run our algorithm. So this is still, maybe this is the end of the theory. But we need some algorithm we can run and get better approximation. Other algorithms, they really implement this algorithm and really achieve a fantastic approximation in the real graph. So our algorithm and this new algorithm is just good in theory. Okay, theory. So here I'm going to explain briefly why previous algorithm gets stuck at 3 here. Okay, so this is the outline. And then once I explain how previous algorithm gets stuck at 3, so you see the sequential algorithm can beat 3, can get 1.437. So definitely they can achieve better approximation here. So there is a method which can. So I'm going to show you how to beat 3 in the sequential setting, give you an idea, and what's the bottleneck if we want to adapt the sequential algorithm to the parallel setting. Okay, and the last part is our idea how to adapt the sequential algorithm to the parallel setting. So why previous work gets stuck at 3 here? Just because all previous algorithm actually tries to parallelize the p-weight algorithm. So this is a very fancy line. So and actually once you know the algorithm, you will say they really give a good line for this algorithm, the p-weight. So if this p-weight algorithm can only provide 3 approximation guarantee here. So what is the p-weight algorithm? So in short, this algorithm is a greedy maximum independent set. So we have a graph. We try to partition the node here. So what we do, at the beginning, we uniformly random choose a node. So here we choose a node D, the purple node D. Then we will put all positive neighbor of this node in the same cluster. So we will include all its positive neighbor, these 3 nodes, to its cluster. And then we remove those cluster nodes and repeat the whole process on the remaining nodes. So this is really just the greedy maximum independent set algorithm. Okay. And then you choose another node. Here we choose another purple node F. We repeat and do it again. So if you remember, for this instance, the optimal solution only has disagreement 4. But here is 5. So this p-weight algorithm makes some mistake. So in some graph, but it can be shown this p-weight algorithm can give us a 3 approximation. So you may wonder, so can we get better? So unfortunately, p-weight algorithm is tight for 3 approximation. So here is an example here. So it's a clique. We only have one negative edge. So it's between this bottom two edge. There is only one negative edge in this graph. So what is the optimal solution for correlation clustering? We put all the nodes in the one cluster. So we only have one disagreement, this negative edge. But if you consider the p-weight algorithm here, what happens? So in most cases, if you do not choose the bottom two node, you will get a very good solution, okay? So in this case, with very high probability, 1 minus 2 over n, this probability, almost 1 probability, we will have a cost of 1 because it's the same as the optimal solution. But with a very tiny probability. So if you are unlucky, choose this bottom node. So this is 2 over n, assume there are n nodes in the graph. With this tiny probability, so the final cluster will exclude exactly one node. So we exclude the other node. This will give us a cost of n minus 2. So it's roughly n. Which means with high probability, with almost 1 probability, we will have a cost of 1. With only 2 over n probability, we will have a cost of n. So in expectation, the total cost is 3. So in this example, and the optimal cost is just 1. So we can never beat 3 for the p-weight algorithm. And all previous algorithms just want to try to parallelize the p-weight algorithm, basically. So they did pretty good. Actually, they even get constant round algorithm. And then how are we going to beat 3 here? So how are we going to get a better than 3 algorithm? So previous sequential algorithm achieve a better approximation. So we definitely can beat 3, but it takes some extra effort. So all previous sequential algorithm almost following this framework. So they design a linear programming. Okay, it might be different linear programming, but here I just show one possible linear programming, and this is one of the most famous linear programming for this problem. And once they have the linear programming, they use the linear programming answer to do the rounding. If you do the rounding, you can get a better solution here. Okay. So I'm going to explain this linear programming a little bit and explain the difficulty of why it's hard to parallelize the algorithm. So this linear programming has a variable for each pair of the node. Okay, each pair of node, we have a variable x, uv. This is not just for positive edge. We also consider the variable for negative edge. Okay, and then this x, you can think this x as the distance between two nodes. If the distance is very small, it's 0, that means we want to put these two nodes together. If the distance is 1, then we want to separate them. So in this example graph, if we already have the cluster here, then we can set the corresponding x value here. So we put these two nodes together, so we set its distance as 0. And we also have this negative edge. So this negative edge, we also put them together, so we will have set it as 0. If we separate two nodes, then we set its distance as 1. That's the linear programming here. So what's the objective for this linear program? So we have some disagreement. The edge becomes wrong. When what? For positive edge, the distance is very large. We separate them. If x is 1, it's very large, and the edge is positive, we have to pay 1 cost. So it's x cost. So the other case is the negative edge. Whenever we have a negative edge here, and we put them together, the distance is 0. We also have 1 cost. So the cost is 1 minus x. So this is the cost for this linear programming. So we can write down the objective. So as the summation of all x for positive edge and summation of 1 minus x for all negative edge. So what is the constraint for this algorithm here? So the constraint, we call it triangle inequality. If you treat this x as a distance, so for every triple, we require what? We require xuw. The distance, the sum of the distance to the third node is greater than the distance itself. So this is the triangle inequality here. Why this is true? That's because whenever this distance xuv is 0, there is no, this constraint won't work here. But whenever xuv is 1, it means we separate this node. So if we separate uv node, let's take an example here. If we separate this xuv, what happens? Consider a third node. uv we separate, so uv will be in different cluster. So either u and w will be in different cluster, or v and w will be in different cluster, which means the summation of this x value, the summation of xuw and xvw, their sum is at least 1. So this is a triangle inequality here. So so once we get this linear programming, what's the next step here? So the next step is modification of the pivot algorithm. The intuition is once we have this x value, the fractional, once we solve the fractional value, this x might be equal to 0 or 0.1, 1/10. This is a really good indicator for our algorithm, for the pivot algorithm. So instead of using pivot algorithm, the greedy maximal independent set algorithm directly, we will use x value as an indicator. So we run the pivot algorithm with just one modification. We randomly choose a node u. So for each edge, for each pair, it's not just edge. For each pair, we will include the node with the probability 1 minus x. Okay, this is the intuition. Since x is a very good indicator, this time if x is very small, x is 0. So we will include this node. If x is very large, is 1, then we will exclude this node. So since the intuition here is x is a good indicator. So what's the problem? What's the difficulty of the sequential algorithm here? So almost all algorithms better than 3 starts with this linear programming or more complicated linear programming. But the problem is we don't know how to solve, in general, this linear programming in no depth. Okay. And actually the state of the SOTA algorithm, I think, takes order square root of n iterations to solve. So this is far away from the Polylog algorithm. So what we do here? So our idea is this is impossible to solve. Maybe I shouldn't say impossible. It's very hard to solve this linear programming in the parallel model. So what we do here, we figure out a method to relax the constraint. We figure out, so when we relax the constraint, we will lose some approximate ratio here since we use less constraint. And then we figure out a way so that we can solve this LP in the parallel model, and also it gives us a good approximation. Okay, this is our main, I think, contribution, what we do. So I'm going to give you an intuition, what we do, how we figure out a way to solve this linear programming in the parallel model. So it's just an idea. I ignore some detail. So we stare at this linear programming for a very long time. So we try to drop this triangle inequality directly. It doesn't work. It will hurt the approximate ratio a lot. So one day we come up with an idea. So actually it's not us. So there is another view of this linear programming. So the left side is the triangle view. So it's just use the triangle inequality as constraint. So the right side is a different view. We call it cut view. So what's the difference? The variable is the same. And the only difference is here is the constraint. Instead of using the triangle, we use a cut constraint. So we consider giving a pair of, this is negative edge, okay? Giving a pair of negative edge. In the triangle inequality, we consider all pair. So, but here, we only consider a pair of negative edge. Then we say that if you cut this negative edge, then you consider all possible paths. This path is all simple paths of positive edge. Okay, this is different from the right side, the left side. The left side might use some negative edge. But here, we only consider all simple paths with positive edge between u and v. So we call this cut. So if we sum up all of this, if we sum up the x value along arbitrary paths, then the cut value is at least the cut for u and v. Okay, so why this is a cut? So if you choose to put UV edge in separate cluster, then we have to at least cut one of the positive edge along a path. That's the intuition, the cut. Okay? So, and actually it doesn't matter so much for the cut view. So since you only need to know this is the cut view of the algorithm. So once you have a cut, we always have a flow, right? The primal, if the primal is the cut, then the dual is the flow. So we will have a corresponding flow for this cut, okay? So for this flow, we need to consider a lot of paths. There might be exponential number of the path here, and then we will send flow along this path. So the path is defined as all simple paths for positive edge between a pair of nodes. It doesn't matter so much. You just need to know this path could be quite long. So we want to send flow along this path and trying to maximize some objective. Okay, that's the flow view. So once we get flow view, we still have no idea how to relax it. We don't know how to do better in parallel. Until one day, so I realized, so if we want to solve the flow RP, what we need to do actually from the ellipsoid method, we need to compute the shortest path. So it's related to shortest path problem. So when the path is very long, then computing this long shortest path in the parallel is very, very expensive. We don't know how to do it. And we realized that we can truncate all paths. We will throw away all paths with long length. So we only consider the path contains 3 edge. That's all we considered in this. So we threw away all other paths, long paths. And what we have is the short path, all length 2 paths of the positive edge between u and v. So now we only need to solve this problem for very short paths. So now it's impossible to solve. And our key observation here is we go through some example and we figure out when we solve this flow problem, so the flow won't use long paths. So mostly it will only use the short path. That's what we get from some example here. So we tried, then we threw away all the long paths. What happened? So if we want to solve this truncated, each iteration we only need to find the maximum set of the shortest path, shortest edge disjoint path. So more exactly, this is a disjoint path with only contains 3 edge. This is 3 edge. Okay. So each path is a positive, negative triangle here. And then each round, we need to figure out a lot of disjoint triangle we assign. I'm not going to talk about the detail, but intuitively, so we assign a weight to the edge, and then we figure out a lot of maximum disjoint triangle. So we want to find the shortest path triangle. There might be a lot. So I'm going to explain one last point here. So why our algorithm takes m to 3 half work here? That's because we consider all the paths with 3 edges. Actually, it's a triangle. So what we need to solve is we need to figure out a lot of positive, and negative triangles. And in the graph, if we consider how many triangles in the graph, it could be up to m to 3 half triangle. So if we want to find a maximum set of such triangle, we have to spend m to 3 half time. You may wonder if there is any other, instead of consider maximum set of such triangle, we consider other type of the triangle. So bad news is, if you want to find one triangle, even if you just want to make one very tiny progress, so it's very hard to beat order m to 3 half under the current framework if you want to even find one triangle. So we show a reduction to the triangle detection problem. So it's believed, this is a conjecture. So no combinatory algorithm can beat m to 3/2, even if you want to find one triangle. Okay, that's it. So that's our algorithm. That's the intuition why we get this low depth runs algorithm. And our algorithm can also implement it in the MPC model. Okay. Oh, sorry.
Questions? Big question. So the LP with the reduction to the two, that has the same value as the original LP, right?
Yes, it's these two LP are the same, exactly the same.
Even after the length 2 reduction.
After the length 2 reduction is not the same. We lose some approximation. So
why is that? Because I mean, from the original LP, also you were only interested in the triangles.
So here, so that's a very good question. More precisely here, if we restrict the path to be length 2 path, then we throw away some triangle here.
Oh, you do throw away triangles?
So yeah, we do throw away some triangle here. So we lose some approximation.
I see.
Yes?
So you said there was an improved algorithm with a better approximation ratio and didn't have the memory requirement and all that for MPC. Do they have similar work?
The total work is actually is very good in theory, so it's sublinear work. So it's order, and you don't have to check all edges in the graph. So you only, but it has a 2 to this polylog 1/epsilon times the n. So it's super good. In theory, super good, I would say.
It's randomized?
It's randomized. So it's an open problem if you can get any deterministic interesting result. So actually, there is no deterministic algorithm can run all of these algorithms are randomized. So if you get some approximation ratio deterministically, that will be super interesting.
Any other questions? Thank you very much.
Okay.